Hello. In this presentation, we'll discuss the mapping of displacements and end actions from one coordinate system to a second coordinate system. This mapping between a local element coordinate system and a global structure coordinate system is accomplished using rotation matrices, which are also known as transformation matrices. Using these rotation or transformation matrices, we'll illustrate an alternative approach to the determination of element stiffness matrices and internal member forces. Let's get started. As a reminder, the matrix analysis approach can be characterized by a structure stiffness matrix K, an associated displacement matrix delta, and a load matrix P. In general, we write the equation that K times delta is equal to P, and the displacements are the unknown quantities. So the overall goal of the matrix analysis process is to develop a set of simultaneous equations that we can solve to find the displacements. When we looked at the member stiffness matrix for a truss element in the first analysis presentation, we calculated it in the context of a global coordinate system, where we have a force in the x direction and a force in the y direction at each end of the member. And then we multiply the stiffness matrix K sub I by the element displacement vector delta sub I to obtain the force vector F sub I. This force vector F sub I is also referred to as the member end actions. The stiffness matrix for that truss element in global coordinates is defined as this, where C and S are the directional cosines for the member, where we have our displacement vector delta and our force vector F defined as shown here when we're working in the global coordinate system. Again, as a reminder, the stiffness coefficient K sub ij is the force at degree of freedom I required to cause a unit displacement at degree of freedom j while all other displacements are held at 0. The stiffness matrices are always symmetric, and the stiffness matrix for a truss element in the global coordinate system is defined as is shown here. For the truss that we have been considering throughout the first two analysis presentations, there are 5 nodes for a total of 10 degrees of freedom, and 7 members, resulting in 7 element or member stiffness matrices. Each structural model has one global coordinate system, as shown here, where the x-axis is horizontal and positive to the right, and the y-axis is vertical and positive upward. In addition to the global coordinate system, each of the elements, and sometimes each of the nodes that make up our model, have their own local coordinate system as well. As you can see on this slide, in addition to the global coordinate system, each of the members that makes up the truss also has its own local coordinate system where the x-axis is positive along the length of the member from the ith node towards the jth node, and the local y-axis is in plane with the positive direction determined using the right-hand rule relative to the local x-axis. I typically use a capital X or capital Y to denote the global coordinate system and a lowercase x or lowercase y to denote the local coordinate system. One of the goals of this presentation is to develop a way to map displacements from one coordinate system to another so that we can work in whichever of the two coordinate systems is more convenient at any given time. My notation is to use a capital K and a capital delta to denote element stiffness matrices and displacements in the global coordinate system, and then use a lowercase k or a lowercase delta to indicate element stiffness matrices or displacements in a local coordinate system. The end displacements, or degrees of freedom, for a truss element are shown on this slide both in the global coordinate system on the left and in the local coordinate system on the right. There are advantages and disadvantages associated with working in either the global coordinate system or the local coordinate system. One of the advantages of working in the local coordinate system is that it's easier to develop element stiffness matrices in the local coordinate system than it is in the global coordinate system. Shown on this slide is the element stiffness matrix for a truss element developed in the local coordinate system. A unit elongation of the member corresponds to the development of a force AE over L, and you can see that that corresponds to the first and the third degrees of freedom associated with this member. The first degree of freedom being delta sub x at the ith end, and the third degree of freedom being delta sub x at the jth end. To develop a mapping from one coordinate system to another, we're going to introduce transformation or rotation matrices, typically denoted with a lowercase gamma or a capital gamma. The lowercase gamma matrix is used to map displacements of a node from one coordinate system to another, whereas the capital gamma matrix is used to map displacements associated with an element from one coordinate system to another. To start off, we'll map nodal displacements in a global coordinate system to displacements in a local coordinate system. As you can see in this slide, global displacements delta capital X and delta capital Y are shown in black. Local displacements delta lowercase x and delta lowercase y are shown in blue, and phi defines the angle between the two coordinate systems. We can use trigonometry to determine the magnitude of the local displacements relative to the global displacements, and next we can collect like terms, resulting in one equation for delta lowercase x as a function of delta uppercase x, delta uppercase y, and phi, and a second equation for delta lowercase y also as a function of delta uppercase x, delta uppercase y, and phi. Finally, we can write these two equations in matrix form, and then we can substitute in our definitions for delta, gamma, and delta. Next, we'll do the same thing, but in the opposite direction. This time, we'll map the nodal displacements in a local coordinate system to displacements in a global coordinate system. On this slide, global displacements delta capital X and delta capital Y are now shown in blue, and local displacements delta lowercase x and delta lowercase y are now shown in black. We can use trigonometry again to determine the magnitude of the global displacements relative to the local displacements. And next we can collect like terms, resulting in one equation for delta capital X as a function of delta lowercase x, delta lowercase y, and phi, and a second equation for delta capital Y as a function of delta lowercase x, delta lowercase y, and phi. Finally, we can write these two equations in matrix form, and then finally substitute in our definitions for the capital delta matrix, lowercase gamma matrix, and lowercase delta matrix. To review, delta is a vector or matrix of displacements in the global coordinate system, the capital XY coordinate system. Lowercase delta is a vector or matrix of displacements in the lowercase XY coordinate system, or the local coordinate system. And lowercase gamma is a transformation matrix or rotation matrix at a point or a node. We note that the lowercase gamma matrix is defined as this: cosine, sine, minus sine, and cosine, and that the inverse of gamma is defined as this, where we have cosine, minus sine, sine, and cosine. We can observe that the inverse of gamma is equal to the transpose of gamma. This is because gamma is an orthogonal matrix, and this property makes it easier for us to map back and forth between two coordinate systems. While it can be useful to map nodal displacements from one coordinate system to another, it would be more useful if we could map member displacements from one coordinate system to another. So while we have developed the rotation matrix, lowercase gamma, for nodal displacements, we still need to develop a rotation matrix, uppercase gamma, for element displacements. For the kth element in a truss, there are two nodes, node I and node J, each with two perpendicular degrees of freedom. And we can write displacements in the local coordinate system, lowercase delta, as a product of the element rotation matrix, capital gamma, and the displacements in the global coordinate system, uppercase delta. Lowercase delta sub k is a 4x1 element displacement matrix in local coordinates for the kth member. Uppercase gamma sub k is a 4x4 element rotation matrix or transformation matrix for the kth member. And uppercase delta sub k is a 4x1 element displacement matrix in global coordinates for the kth member. We can substitute the matrices lowercase delta, lowercase gamma, and uppercase delta into this equation, which gives us an equation with matrices of matrices, where delta sub I and delta sub j are each 2x1 nodal displacement matrices in local coordinates for nodes I and j respectively. And finally, if we substitute for these matrices, we're left with this form of the transformation where delta lowercase x and delta lowercase y are scalar displacements in the local coordinates, and delta uppercase x and delta uppercase y are scalar displacements in global coordinates. Recall that for the overall structure, we can write the equation that k times delta is equal to p. Correspondingly, for each of the elements or members in the structure, we can write the same equation either in global coordinates or in local coordinates. Finally, based on the rotation or transformation matrices that we've just derived, we can write that the member end actions in local coordinates are equal to the rotation matrix capital gamma times the member end actions in global coordinates, or that the member end displacements in local coordinates, lowercase delta, is equal to the transformation matrix capital gamma times the member end displacements in global coordinates, capital delta. Starting with this formulation in local coordinates for the kth element, we can first observe that little f is equal to capital gamma times big F. Next, we substitute capital gamma times capital delta for lowercase delta and solve for big F. Then we can substitute the transpose of capital gamma for the inverse of capital gamma and observe that big K must be equal to the product of the transpose of capital gamma, little k, and capital gamma. In other words, the element stiffness matrix in global coordinates is equal to gamma transpose times the element stiffness matrix in local coordinates times gamma. This process is referred to as pre- and post-multiplication. Considering the ith Truss element stiffness matrix in local coordinates, where we know the element stiffness matrix is this, we can determine the element stiffness matrix in global coordinates by pre- and post-multiplying by the rotation matrix. Substituting in for gamma and k, we end up with this for our element stiffness matrix in global coordinates, where c represents the cosine of phi and s represents the sine of phi. Expanding that equation with three matrices, you'll see that we end up with the same element stiffness matrix in global coordinates that we derived directly in the first analysis presentation. For truss elements, it makes little difference whether the element stiffness matrix is derived in the global coordinate system or whether we first derive the element stiffness matrix in local coordinate system and then use pre- and post multiplication to solve for the stiffness matrix in the global coordinate system. However, for frame elements, the process of deriving the element stiffness matrix directly in the global coordinate system would be very challenging. Thus, for frame elements, it's much simpler to derive the element stiffness matrix first in the local coordinate system and then use the pre- and post multiplication process to convert that to the global coordinate system. So bottom line, we've illustrated this process for truss elements, but it's really more advantageous when we get to frame elements instead. After we've determined the stiffness matrix for each of the elements in our structure and have assembled the global stiffness matrix and then gone through the process of solving for the global nodal displacements, we use the process of back substitution to solve for the member end actions and then finally for the member internal forces. The matrix capital F sub I represents the member end actions for the ith member. Ultimately, for the truss element, we're after the internal member force P. If there are no loads applied to the member between the nodes, then the axial force in the member is constant, and we can solve for P by considering a free body diagram of either of the two nodes. Thus, we determine P by using F sub x and the cosine of phi, or for the case where phi is equal to 90 degrees, we can determine P by using F sub y and the sine of phi. Alternatively, we can transform the member end actions from the global coordinate system to the local coordinate system, and then using this relationship that we derived earlier, where lowercase f is the end actions of the member in the local coordinate system, we can again use a free body diagram of either of the two nodes at the ends of the member and solve for P as a function of either f sub x2 or negative f sub x1, as is shown here. In conclusion, this slide outlines the process for the matrix analysis of a 2D truss with member stiffness formulated in the global coordinates. First, we identify and label the degrees of freedom at each node. And second, we formulate the stiffness matrix for each of the members in the truss. Next, we expand each of the member stiffness matrices to include all of the structured degrees of freedom, and then assemble the global stiffness matrix K. After that, we assemble the nodal load matrix P, then reorder and partition the global stiffness matrix K and the nodal load matrix P, and then we solve for the displacements at the free degrees of freedom. Next, we solve for the structure reactions as needed, and then finally back multiply to find the member end actions and solve for the internal member actions as needed. The process for the matrix analysis of a 2D truss with member stiffness formulated in local coordinates is very similar to the process with member stiffness formulated in global coordinates, with the exceptions that, first, the pre- and post-multiplication process is used to determine the element stiffness in global coordinates, and second, the member end actions are transformed to the local coordinates before solving for the internal member forces.